All right, thanks for the introduction, Lex. All right, thanks for coming to my talk. I will tell you about some work we've done over the past year on meta-learning and self-play at OpenAI. And before I dive into some of the more technical details of the work, I want to spend a little bit of time talking about deep learning and why it works at all in the first place, which I think it's actually not a self-evident thing that they should work. One fact, it's actually a fact, it's a mathematical theorem that you can prove, is that if you could find the shortest program that does very, very well on your data, then you will achieve the best generalization possible. With a little bit of modification, you can turn it into a precise theorem. And on a very intuitive level, it's easy to see why it should be the case. If you have some data and you're able to find the shorter program which generates this data, then you've essentially extracted all conceivable regularity from this data into your program. And then you can use this object to make the best predictions possible. Like if you have data which is so complex that there is no way to express it as a shorter program, then it means that your data is totally random. There is no way to extract any regularity from it whatsoever. Now, there is little known mathematical theory behind this, and the proofs of these statements are actually not even that hard. But the one minor slight disappointment is that it's actually not possible, at least given today's tools and understanding, to find the best short program that explains or generates or solves your problem given your data. This problem is computationally intractable. The space of all programs is a very nasty space. Small changes to your program result in massive changes to the behavior of the program, as it should be. It makes sense. You have a loop, you change the inside of the loop. Of course, you get something totally different. So the space of programs is so hard, at least given what we know today, search there seems to be completely off the table. Well, if we give up on short programs, what about small circuits? Well, it turns out that we are lucky. It turns out that when it comes to small circuits, you can just find the best small circuit that solves your problem using backpropagation. And this is the miraculous fact on which the rest of AI stands. It is the fact that when you have a circuit and you impose constraints on your circuit using data, you can find a way to satisfy these constraints using backprop by iteratively making small changes to the weights of your neural network until its predictions satisfy the data. What this means is that the computational problem that's solved by backpropagation is extremely profound. It is circuit search. Now, we know that you can't solve it always, but you can solve it sometimes. And you can solve it at those times where we have a practical data set. It is easy to design artificial data sets for which you cannot find the best neural network. But in practice, that seems to be not a problem. Like you can think of training a neural network as solving a neural equation in many cases where you have a large number of equation terms like this, f of xi theta equals yi. So you've got your parameters and they represent all your degrees of freedom. And you use gradient descent to push the information from these equations into the parameters to satisfy them all. And you can see that the neural network, let's say one with 50 layers, is basically a parallel computer that is given 50 time steps to run. And you can do quite a lot with 50 time steps of a very, very powerful, massively parallel computer. So for example, I think it is not widely known that you can learn to sort n-bit numbers using a modestly sized neural network with just 2 hidden layers, which is not bad. It's not self-evident, especially since we've been taught that sorting requires log n parallel steps. With a neural network, you can sort successfully using only 2 parallel steps. So there's something slightly non-obvious going on. Now, these are parallel steps of threshold neurons, so they're doing a little bit more work. That's the answer to the mystery. But if you got 50 such layers, you can do quite a bit of logic, quite a bit of reasoning, all inside the neural network. And that's why it works. Given the data, we are able to find the best neural network. And because the neural network is deep, because it can run computation inside of its layers, the best neural network is worth finding. Because that's really what you need. You need a model class which is worth optimizing. But it also needs to be optimizable. And deep neural networks satisfy both of these constraints. And this is why everything works. This is the basis on which everything else resides. Now I want to talk a little bit about reinforcement learning. So reinforcement learning is a framework. It's a framework of evaluating agents in their ability to achieve goals in complicated stochastic environments. You got an agent which is plugged into an environment, as shown in the figure right here. And for any given agent, you can simply run it many times and compute its average reward. Now, the thing that's interesting about the reinforcement learning framework is that there exist interesting, useful reinforcement learning algorithms. The framework existed for a long time. It became interesting once we realized that good algorithms exist. Now, they're not perfect algorithms, but they are good enough to do interesting things. And all you want, the mathematical problem, is one where you need to maximize the expected reward. Now, one important way in which the reinforcement learning framework is not quite complete is that it assumes that the reward is given by the environment. You see this picture. The agent sends an action, while the reward sends it an observation and both the observation and the reward backwards. That's what the environment communicates back. The way in which this is not the case in the real world is that we figure out what the reward is from the observation. We reward ourselves. We are not told, the environment doesn't say, hey, here's some negative reward. It's our interpretation of our senses that lets us determine what the reward is. And there is only one real true reward in life, and this is existence or non-existence. And everything else is a corollary of that. So, well, what should our agent be? You already know the answer. It should be a neural network. Because whenever you want to do something, the answer is going to be a neural network, and you want the agent to map observations to actions. So you let it be parameterized with a neural net, and you apply a learning algorithm. So I want to explain to you how reinforcement learning works. This is model-free reinforcement learning. The reinforcement learning that's actually being used in practice everywhere. But it's also it's very robust, it's very simple. It's also not very efficient. So the way it works is the following. This is literally the one-sentence description of what happens. In short, try something new. Add randomness to your actions. And compare the result to your expectation. If the result surprises you, if you find that the result exceeded your expectation, then change your parameters to take those actions in the future. That's it. This is the full idea of reinforcement learning. Try it out, see if you like it, and if you do, do more of that in the future. And that's it. That's literally it. This is the core idea. Now, it turns out it's not difficult to formalize mathematically. But this is really what's going on. If in a neural network, in a regular neural network, like this, you might say, okay, what's the goal? You run the neural network, you get an answer. You compare it to the desired answer. And whatever difference you have between those two, you send it back to change the neural network. That's supervised learning. In reinforcement learning, you run a neural network, you add a bit of randomness to your action, and then if you like the result, your randomness turns into the desired target, in effect. So that's it. Trivial. Now, math exists. Without explaining what these equations mean, the point is not really to derive them, but just to show that they exist. There are two classes of reinforcement learning algorithms. One of them is the policy gradient, where basically what you do is that you take this expression right there, the sum of rewards, and you just crunch through the derivatives. You expand the terms, you do some algebra, and you get a derivative. And miraculously, the derivative has exactly the form that I told you, which is try some actions, and if you like them, increase the log probability of the actions. That literally follows from the math. It's very nice when the intuitive explanation has a one-to-one correspondence to what you get in the equation, even though you'll have to take my word for it if you're not familiar with it. That's the equation at the top. Then there is a different class of reinforcement learning algorithms, which is a little bit more difficult to explain. It's called the Q-learning-based algorithms. They are a bit less stable, a bit more sample efficient, and it has the property that it can learn not only from the data generated by the actor, but from any other data as well. So it has a different robustness profile, which should be a little bit important, but it's only going to be a technicality. So yeah, this is the on-policy, off-policy distinction, but it's a little bit technical, so if you find this hard to understand, don't worry about it. If you already know it, then you already know it. So now what's the potential of reinforcement learning? What's the promise? What is it actually? Why should we be excited about it? Now, there are two reasons. The reinforcement learning algorithms of today are already useful and interesting, and especially if you have a really good simulation of your world, you could train agents to do lots of interesting things. But what's really exciting is if you can build a super amazing sample efficient reinforcement learning algorithm. We just give it a tiny amount of data, and the algorithm just crunches through it and extracts every bit of entropy out of it in order to learn in the fastest way possible. Now, today our algorithms are not particularly data efficient. They are data inefficient. But as our field keeps making progress, this will change. Next, I want to dive into the topic of meta-learning. The goal of meta-learning. So, meta-learning is a beautiful idea that doesn't really work, but it kind of works. And it's really promising too. It's another promising idea. So what's the dream? We have some learning algorithms. Perhaps we could use those learning algorithms in order to learn to learn. That'd be nice if we could learn to learn. So how would you do that? You would take a system which you train it not on one task, but on many tasks. And you ask it that it learns to solve these tasks quickly. And that may actually be enough. So here's how it looks like. Here's how most traditional meta-learning looks like. You have a model which is a big neural network. But what you do is that you treat instead of training cases, you have training tasks. And instead of test cases, you have test tasks. So your input may be, instead of just your current test case, it would be all the information about the test tasks plus the test case. And you'll try to output the prediction or action for that test case. So basically you say, yeah, I'm going to give you your 10 examples as part of your input to your model. Figure out how to make the best use of them. So it's a really straightforward idea. You turn the neural network into the learning algorithm by turning a training task into a training case. So training task equals training case. This is meta-learning. This one sentence. And so there have been several success stories which I think are very interesting. One of the success stories of meta-learning is learning to recognize characters quickly. So there have been a data set produced by MIT by Lake et al. And this is a data set where you have a large number of different handwritten characters. And people have been able to train extremely strong meta-learning system for this task. Another very successful example of meta-learning is that of neural architecture search by Zop and Lee from Google, where they found a neural architecture that solved one problem well, a small problem, and then you could generalize, and then it would successfully solve large problems as well. So this is the kind of the small number of bits meta-learning. It's like when you learn the architecture, or maybe even learn a small program or learning algorithm, which you apply to new tasks. So this is the other way of doing meta-learning. So anyway, but the point is, what's really happening in meta-learning in most cases is that you turn a training task into a training case and pretend that this is totally normal deep learning. That's it. This is the entirety of meta-learning. Everything else is just minor details. Next, I want to dive in. So now that I finished the introduction section, I want to start discussing different work by different people from OpenAI. And I want to start by talking about Hindsight experience replay. There's been a large effort by Andrihovic et al. To develop a learning algorithm for reinforcement learning that doesn't solve just one task, but it solves many tasks, and it learns to make use of its experience in a much more efficient way. And I want to discuss one problem in reinforcement learning. It's actually, I guess, a set of problems which are all related to each other. Like one really important thing you need to learn to do is to explore. You start out in an environment, you don't know what to do. What do you do? So one very important thing that has to happen is that you must get rewards from time to time. If you try something and you don't get rewards, then how can you learn? So I said that's the kind of the crux of the problem. How do you learn? And relatedly, is there any way to meaningfully benefit from the experience, from your attempts from your failures? If you try to achieve a goal and you fail, can you still learn from it? Instead of asking your algorithm to achieve a single goal, you want to learn a policy that can achieve a very large family of goals. For example, instead of reaching one state, you want to learn a policy that reaches every state of your system. Now, what's the implication? Anytime you do something, you achieve some state. So let's suppose you say, I want to achieve state A. I try my best, and I end up achieving state B. I can either conclude, well, that was disappointing, I haven't learned almost anything. I still have no idea how to achieve state A. But alternatively, I can say, well, wait a second, I've just reached a perfectly good state, which is B. Can I learn how to achieve state B from my attempt to achieve state A? And the answer is yes, you can. And it just works. And I just want to point out, this is the one case, there's a small subtlety here which may be interesting to those of you who are very familiar with the distinction between on-policy and off-policy. When you try to achieve A, you're doing on-policy learning for reaching the state A, but you're doing off-policy learning for reaching the state B, because you would take different actions if you would actually try to reach state B. So that's why it's very important that the algorithm you use here can support off-policy learning. But that's a minor technicality. At the crux of the idea is you make the problem easier by ostensibly making it harder. By training a system which aspires to learn to reach every state, to learn to achieve every goal, to learn to master its environment in general, you build a system which always learns something. It learns from success as well as from failure. Because if it tries to do one thing and it does something else, it now has training data for how to achieve that something else. I want to show you a video of how this thing works in practice. So one challenge in reinforcement learning systems is the need to shape the reward. So what does it mean? It means that at the beginning of the system, at the start of learning, when the system doesn't know much, it will probably not achieve your goal. And so it's important that you design your reward function to give it gradual increments, to make it smooth and continuous, so that even when the system is not very good, it achieves the goal. Now, if you give your system a very sparse reward, where the reward is achieved only when you reach a final state, then it becomes very hard for normal reinforcement learning algorithms to solve a problem, because naturally, you never get the reward, so you never learn. No reward means no learning. But here, because you learn from failure as well as from success, this problem simply doesn't occur. And so this is nice. I think, let's look at the videos a little bit more. Like it's nice how it confidently and energetically moves the little green puck to its target. And here's another one. Okay, so we can skip the physics. It works on the physics if you do it on a physical robot as well, but we can skip it. So I think the point is that the hindsight experience replay algorithm is directionally correct because you want to make use of all your data and not only a small fraction of it. Now, one huge question is, where do you get the high-level states? Where do the high-level states come from? Because in the work that I've shown you so far, the system is asked to achieve low-level states. So I think one thing that will become very important for these kind of approaches is representation learning and unsupervised learning. Figure out what are the right states, what's the state space of goals that's worth achieving. Now I want to go through some real meta-learning results. And I'll show you a very simple way of doing sim to real from simulation to the physical robot with meta-learning. And this is work by Peng et al. It was a really nice intern project in 2017. So, I think we can agree that in the domain of robotics, it would be nice if you could train your policy in simulation, and then somehow this knowledge would carry over to the physical robot. Now, we can build simulators that are okay, but they can never perfectly match the real world unless you want to have an insanely slow simulator. And the reason for that is that it turns out that simulating contacts is super hard. And I heard somewhere, correct me if I'm wrong, that simulating friction is NP-complete. I'm not sure. But it's like stuff like that. So your simulation is just not going to match reality. There'll be some resemblance, but that's it. How can we address this problem? And I want to show you one simple idea. So let's say one thing that would be nice is that if you could learn a policy that would quickly adapt itself to the real world. Well, if you want to learn a policy that can quickly adapt, we need to make sure that it has opportunities to adapt during training time. So what do? Instead of solving our problem in just one simulator, we add a huge amount of variability to the simulator. We say, we will randomize the frictions, we will randomize the masses, the length of the different objects and their, dimensions. So you try to randomize physics, the simulator, in lots of different ways. And then importantly, you don't tell the policy how you randomized it. So what is it going to do then? You take your policy and you put it in an environment and it says, well, this is really tough. I don't know what the masses are and I don't know what the frictions are. I need to try things out and figure out what the friction is as I get responses from the environment. So you learn a certain degree of adaptability into the policy. And it actually works. I just want to show you. This is what happens when you just train a policy in simulation and deploy it on the physical robot. And here the goal is to bring the hockey puck towards the red dot. And you will see that it will struggle. And the reason it struggles is because of the systematic differences between the simulator and the real physical robot. So even the basic movement is difficult for the policy because the assumptions are violated so much. So if you do the training as I discussed, we train a recurrent neural network policy which learns to quickly infer properties of the simulator in order to accomplish the task. You can then give it the real thing, the real physics, and it will do much better. So now this is not a perfect technique, but it's definitely very promising. It's promising whenever you are able to sufficiently randomize the simulator. So it's definitely very nice to see the closed loop nature of the policy. You can see that it would push the hockey puck and it would correct it very, very gently to bring it to the goal. Yeah, you saw that? That was cool. So that was a cool application of meta-learning. I want to discuss one more application of meta-learning, which is learning a hierarchy of actions. And this was work done by Franz et al. Actually, Kevin Franz, the intern who did it, was in high school when he wrote this paper. So one thing that would be nice is if reinforcement learning was hierarchical. If instead of simply taking micro actions, you had some kind of little subroutines that you could deploy. Maybe the term subroutine is a little bit too crude, but if you had some idea of which action primitives are worth starting with. Now, no one has been able to get actually like real value add from hierarchical reinforcement learning yet. So far, all the really cool results, all the really convincing results of reinforcement learning do not use it. And that's because we haven't quite figured out what's the right way for reinforcement learning, for hierarchical reinforcement learning. And I just want to show you one very simple approach where you use meta-learning to learn a hierarchy of actions. So here's what you do. You have, in this specific work, you have a certain, let's say you have a certain number of low-level primitives. Let's say you have 10 of them. And you have a distribution of tasks. And your goal is to learn low-level primitives such that when they are used inside a very brief run of some reinforcement learning algorithm, you will make as much progress as possible. So the idea is you want to get the greatest amount of progress. You want to learn policies that result in you want to learn primitives that result in the greatest amount of progress possible when used inside learning. So this is a meta-learning setup because you need distribution of tasks. And here we've had a little maze. You have a distribution of mazes, and in this case, the little bug learned 3 policies which move it in a fixed direction. And as a result of having this hierarchy, you're able to solve problems really fast, but only when the hierarchy is correct. So hierarchical reinforcement learning is still work in progress, and this work is an interesting proof point of how hierarchical reinforcement could be like, how hierarchical reinforcement learning could be like if it worked. Now, I want to just spend one slide addressing the limitations of high-capacity method learning. The specific limitation is that the training task distribution has to be equal to the test task distribution. And I think this is a real limitation because in reality, the new task that you want to learn will in some ways be fundamentally different from anything you've seen so far. So for example, if you go to school, you learn lots of useful things. But then when you go to work, only a fraction of the things that you've learned carries over. You need to learn quite a few more things from scratch. So meta-learning would struggle with that because it really assumes that the training data is, that the distribution over the training task has to be equal to the distribution over the test tasks. So that's a limitation. I think that as we develop better algorithms for being robust when the test tasks are outside of the distribution of the training task, then meta-learning will work much better. Now, I want to talk about self-play. I think self-play is a very cool topic that's starting to get attention only now. And I want to start by reviewing very old work called TD Gammon. It's back from all the way from 1992, so it's 26 years old now. It was done by Jerry Tesauro. So this work is really incredible because it has so much relevance today. What they did basically, they said, okay, let's take 2 neural networks and let them play against each other, let them play backgammon against each other, and let them be trained with Q-learning. So it's a super modern approach. And you would think this was a paper from 2017, except that when you look at this plot, it shows that you only have 10 hidden units, 20 hidden units, 40 and 80 for the different colors, where you notice that the largest neural network works best. So in some ways, not much has changed, and this is the evidence. And in fact, they were able to beat the world champion in backgammon, and they were able to discover new strategies that the best human backgammon players have not noticed. And they've determined that the strategies discovered by TD Gammon are actually better. So that's pure self-play with Q-learning, which remained dormant until the DQ and work with Atari by DeepMind. So, now other examples of self-play include AlphaGo 0, which was able to learn to beat the world champion in Go without using any external data whatsoever. Another result of this vein is by OpenAI, which is our Dota 2 bot, which was able to build the world champion on the 1v1 version of the game.